Figured it like this.
All right. Shall we start? Okay, so reductions, hardness. I've been sensing a lot of confusion and just sort of what on earth is going on here with regarding reductions. So I thought maybe I'll take a few minutes to recap how we prove lower bounds on the complex fiber problem, as opposed to all this time we're proving upper bounds on the complex fiber problem. I think the source of this confusion, and by the way, every year when I teach this class, there's the same kind of confusion. So it's quite normal to be confused the first time you see this. Is because we're used to thinking, this kind of a backwards way of thinking about algorithm design. Because normally you think about algorithm design as, okay, I want to solve this problem, I express it in terms of subroutines that are much easier, I solve the subroutines and I solve the problem. And we're kind of using the same principle, but we're doing it backwards. And that, I think, makes things, or possibly makes things very confusing. So, if you think of a normal sort of, I have some kind of problem, let's call this P. Right? And I want to solve it. Right? I don't know how to solve it, but I want to solve it. And so, I'm going to try and express it in terms of subroutine. So I have some kind of subroutine. Solve P. Then I do a bunch of code. And inside that code, I invoked solve Q, right? And then I get the output of Q. This gives me some answer, and I can return a solution to P. So this is my algorithm, in some sense, for solving P, right? And it works because when I call solve Q, I'm calling some other routine which I know how to write, right? Which is solve Q. Right? When you write code, this is what you're doing. You're taking your problem, you're thinking about it hard, and you're breaking it down into simpler pieces. You're solving the simpler pieces and doing it. So, in other words, you can write down something like this, which says P is, I'll put in quotes, easy. And when I say easier, I only mean you can solve it. I don't mean it's really easy. Because right? And you're very familiar with this kind of idea, right? In order to solve P and to make it easy, I somehow need to convert it into Q. And maybe there's a Q1, a Q2, a Q3, or maybe I call Q 10 times, I don't know, or whatever. I have to call some Qs which are easy. I know them to be easy. And that allows me to compute that easy. Right? This is how you would normally write code with use of this. Of course, in our case, we're doing something which looks the same but is very different. So once again, we have this picture. So again, we have some picture where we want to solve P. And we write some code. And in the middle of the code, we realize that, oh, look, in order to solve P, I want to call solve Q. And this will return the solution here, right? Just like before. Except there's one difference here. That in the first case, the problem we wanted to solve was P. In the second case, the problem we're trying to prove hard is Q. And that's where things start getting weird, right? When we want to say that we're trying to show that problem Q is hard, we're actually invoking where we were solving P using Q. Remember, the rationale was that P was easy because Q was easy. But suppose I know that P is actually hard. someone told me, no, P is actually quite hard. I shouldn't be able to do this. Right? Because someone told me P is hard, there's no way to do this. The only way to resolve that problem is if Q was actually not easy. Because then I have not changed the world in some string. And this is the essence of a reduction. That when we are trying to say that Q is hard, what we're going to do is solve some problem P using Q and rely on the fact that P has been told to us to be hard. And in fact, so if you think of the contrapositive of this, what we're saying is that so it's the same mechanics that you use when you want to solve a problem, but you use it backwards. And at least in my view, and I could be wrong here, this is why I think it causes some cognitive confusion, because you're used to thinking of this, but you really should be thinking of that. And I've seen this happen whenever I talk about lower bounds, and this is not just in an intro algorithms class or intro grad class, even in advanced seminars where we talk about lower bounds, this kind of flip takes some time getting used to. For those of you in the communication complexity class, in seminar we had this discussion a few weeks ago or maybe last week about this whole business of how you prove lower bounds. So, are there any questions about this? This is very important to internalize this kind of flipping around that we're doing here, because all your reductions are going to go through this argument, and if you are not sure about this, it will be very hard for you to see how these reductions work. And I don't expect that you'll go into this class knowing, being experts in how to prove that problems are NP hard. But it's useful to know how it works, right? And to know that, okay, one day if you have to show a problem is hard, there is a way to do it. You may not remember it, you have to go look at a book, ask someone else, but at least you know that there's a way to do it, and this is the reasoning behind it. Any questions? And I'm going to go through a number of examples now, so if you want to see more concrete examples, we'll go through that. But it's important to get this bigger picture.
Can we say every NP hard problem is NP?
That's not true. Being NP hard and being an NP are two different things. Being NP complete is the thing that puts them two together. They're two different concepts. Remember, being NP hard is a bad news statement. It's like, oh my god, this problem is really hard. Being an NP is a good news statement. Oh good, I can verify this problem nicely. So they're two different statements altogether about a problem. One says it's really bad, one says it's not so bad. NP completeness gets you the sandwich of the two things. This and that. So that's what they're different. Yes?
You're continuing the same argument in both the cases, if that is the case. So when you start solving P and you realize that you need the solution for Q in between, you need to solve Q basically.
In this case here?
No, second case. I mean, I'm continuing the same ideology in this also.
Okay, so I'm beginning to solve P and I realize I need to solve Q.
Q, yeah.
It's not so much that I need to solve Q, it's that I can use Q to solve P. It's a choice I'm making.
Yeah.
It's not a requirement.
So, I mean, still, I intuitively think like, okay, if I realize when I'm solving Q to solve P, that Q was hard to solve, that is why I concluded that P was hard. So, I mean,
Oh, that's how you're getting to that wrong reasoning is what you're saying.
Yeah.
The problem is you're assuming that was the only way to solve it. That's the flaw in your reasoning. Your reasoning assumes that all paths to solving P go through Q.
Yes.
That's not what I'm saying here. I'm saying, oh, let's choose a path that happens to go through Q. And you come back to the left side, right? You chose to solve P by using a Q subroutine. You could have chosen a different subroutine. You could have done it a different way. There may be maybe 5 different ways to solve this problem P. Right? You happen to choose Q. It's not that you had no choice but to choose Q. You chose it. Similarly here, there's a choice involved. Your flawed reasoning requires you to say that there is no choice. There is only one way to solve P. It goes through Q. So if I prove Q hard, P is hard. So you're asking for a much stronger statement. If you could do that, then yes, your reasoning would be correct. But it's way harder to say that there is only all the ways to solve P must go through Q. And that maybe is how you get to that, I wouldn't say flawed reasoning, but reasoning that doesn't help in this case. The reasons of choice.
So for this case, when you say Q is hard if P is hard, that you are given the problem P is hard.
Yeah, because I'm just doing the contrapositive of this. I should have written here to be more precise. I should say so this is just a contrapositive meaning. You know, if A implies B, then not B implies not A. Is what I'm using. Any other questions about this? And again, don't worry if it feels kind of fuzzy around the edges. That's normal. Hopefully, as you go through examples, it'll start getting a little bit clearer. These are not concepts that you just get in much. Take a bit of time to use. Okay, let's do some examples. And I'm going to these examples again in a somewhat stylized way because there's pretty much, there are 2 or 3 different ways to do a reduction, and they all follow the same general format. So if you keep the format in your head, you have a template, and then you can just keep applying the template. So the first one we're going to do. So you remember this problem called SAT. So let's say, I have a problem called SAT. If you remember, SAT was a problem of, so this is the problem, and the instance is collection of clauses. So let's call them C1 and C2 up to Cm. Each clause disjunction of variables. So Cj is equal to xj1 or xj2 or maybe xj3 and so on. And each xij is either some variable, let's call it vk or not vk. Okay? That's the instance. That's what the input to SAT problem looks like. The question is, does there exist a true and false assignment to variables vi? And let's say there are n variables such that the AND of all the CI is true, right? This is a well-defined problem. There's an instance. This is what the input looks like. This is what the question is. Yes? And we kind of informally showed last time that SAT was NP-hard by showing that you could reduce circuit SAT, which was the UR NP-hard problem, the first one, to SAT. Just by realizing that you can take every Boolean gate and convert this into a set of columns. Okay, we did this very informally. SAT is also an NP because if I gave you the answer, does there exist? If I give you a true false assignment, you can quickly scan all the clauses and make sure in linear time that in fact there's a satisfying, that in fact the clauses are all true, that that each of the clauses is true. Okay, all right. So SAT is NP complete. But it turns out that for many problems, it's more convenient to work with a simplified version of SAT, which we'll call 3SAT. I'm just going to write 3SAT right here. Because it's going to be basically the same as SAT. Except each clause has exactly 3. I'm going to actually call these, not just to be clear, I'm going to call them literals, just to distinguish from variables. Okay? So I don't have this big long line of literals in the clause, I have exactly 3. it turned out to be more convenient to work this way. Of course, having done that, it is no longer clear whether this problem is still NP complete. It's still an NP, that doesn't change anything, because that's a good news situation. Making the problem easier, or making the problem different, does not change that, but is it still hard? I don't know. It's not obvious at all, because it's a special case of that. When you special case a problem, you might make it easier, or you might not. So now we have to figure out whether the 3-SAT is hard or not. And so we're going to prove that 3-SAT is NP hard by reduction. And so we're going to do a reduction from SAT to 3-SAT, and that will give us the proof we want. Right? If you have an unknown problem, you take the known problem and reduce it to the unknown problem. Okay. So the 3-SAT instance in question look pretty much the same as the SAT instance in question. So in order to construct a reduction from SAT to 3-SAT, what do we need to do? We need to find a way to take an arbitrary instance of SAT, anything we get, and rearrange the inputs so that they look like a syntactically correct input to 3-SAT. And then you have to show that the truth value remains the same, obviously. A yes becomes a yes, and no becomes a no, or vice versa, whatever. But it has to be easy to, you're going to be able to predict the output from here. Okay, so how do we do this? Any thoughts? Yes?
You try taking the bigger clauses and breaking them up.
Breaking them up, right?
Yeah, I was just going to say the same. They're associatives. You do them in any order, so you can do the first. They're associatives, so you could do 3 of them at the same time and have do 2 more.
Yep.
And then keep going.
Okay, so that's a good idea. So we have these big long clauses. That seems to be the only issue here. Let's break them up. Okay. So let's say I have, so take some clause. And let's say it consists of literals x1 or x2 up to xk. And again, I distinguish literals from variables because literals are just a variable but not maybe on the middle. So the fact that I will put a negation doesn't mean, it just means that it's inside the definition. And if there's k of them, I just rewrite it as, you know, c1 or and c2 and c3, let's say. In this case, so let's say for example this is equal to x1 or x2 or x3 or x4 or x5. So we'll break up our process into 2 problems. One is to get them to 3 or below, and then to get them exactly 3. Okay, so let's at least get 3 or below. That seems like a harder thing to do. So then you can break this up as we'll have 2 clauses. So what you'd want to do, or what sounds like you're suggesting to do, is something like this. Is that what you're suggesting? I just broke them up. Doesn't quite work, does it?
No, not quite yet, because you still have to or.
So how do I do it? So what you want to do, I think, what I did not do, what you wanted to do, was do this.
Right. That should give you C.
Yes, but we have a problem. That's not what the input looks like. The input requires you to have a collection of ands of clauses.
Well, you solved for CI, and now we have other C's that we can.
I know, but I taken CI, and I've replaced CI by the or of 2 clauses. But now, I want ands everywhere. So what am I going to do?
You just distribute.
You just distribute. Okay. So that's a good idea. So if you have a distribution, what you're saying is that if now I have, so it looks like this, right? I had, let's say C1, go away. What is it? And C2. This has now become, well, this has become C11 or C2, C12, and C2, right? So now we can rewrite this as C11 and C2, or C12 and C2. And I can keep doing this. Eventually I'll get everything inside. The problem is that, think of a simple example. Suppose I have clauses that look like this. CI1 or CI2 and C, K1 or CJ2 and keep going. Let's say there are m of these because there are m clauses to begin with. When I multiply everything out, I'm going to get 2, 3m different things. And that's no good because my reduction has to work in polynomial form. Yes?
We use De Morgan's law to like.
I am using De Morgan's law.
Oh, okay.
That's exactly what I'm using. I'm trying to use De Morgan's law, but it's going to blow things up.
All right.
But you want to find one solution, right? All I have to take is one of the two to the power m different things and then find
Which
it.
one?
Once I make them into
Yeah.
all of them, like let's say the clause is D1 or D2 or something like that, 2 to the power m I have.
Yeah.
I take D1 and then find literals such a way that only D1 is 1.
How do you know that? You don't know what the solution to the SAT looks like. I told you I'm transforming the instance, not the solution. I don't know what the solution to SAT is. In fact, I can't solve SAT. I'm trying to solve SAT using 3 SAT. So I have to do it in a way that no matter what the answer is, I get the same answer here.
Would you somehow create new variables or?
Sure, you can, but how?
I know.
But that, I figure out the right track. That's one way to do it. So the question is this. So here's an idea. Here's what I'm going to do. Let's go back to my example again. I have 5 things. I'm going to rewrite this as I introduce a new variable n1. My new output is syntactically correct. It is a collection of clauses that are added together. Each clause has exactly 3 things in it. So the syntax is correct. But does it have the same truth value as the original clause? What I require is that no matter what assignment of values I put on the original clause, I get the same assignment here, regardless of the value of n1. So let's think of it this way. When would the first clause be true?
At least one is true.
If at least one of them is true. Okay? Okay. Is there a way to make the second clause true if one of them is true? Well, suppose x1 is true. Then x1 is fine. How do you make x2 true though? Because there's no, how do you, suppose my satisfying instance was 1 and all zeros. Now I have to satisfy 2 clauses here, not 1. What do I do?
N1 false.
You make n1 false. Because now if think of it this way. Suppose I want to make this true, so this is 1, this is going to be 0, this is going to be 0, this is going to be 0. My original clause is true, but this is not. But since this clause is true already, I don't care what this value is, I can make it a 0. Which automatically makes this a 1. And now this is true.
What happened to X3?
Sorry?
X3.
I managed to drop it. Just for clarity, let's pretend we don't have an x3 right now because I have a clause for that. But you're good catch. I'll tell you what happens when you do an x3. Those x3s are important. So you see what I did here? I added an auxiliary variable, but I had to be very careful about it because I don't want it to start messing things up. So now one direction is true. If I do have a truth value of 1, in the first case, I can do something in the second case. And obviously, you can do the other way around, right? If x4 happened to be the one that was 1, then you set n1 bar to be 0, which means n1 becomes 1 and you can do the same way. So if the first clause is true, you can find a solution where the second clause is true. Suppose the first clause is false. Could you accidentally make the second clause true? The second set of clauses true? So the first one is false, they're all 0, right? So this is the second case. If they're all 0, is there any way to satisfy both these clauses now? No, because if you set n1 to 1, its complement will be 0. One of the two clauses will be get nuked. And you need both of them to be 1. So if the original clause is 1, then there exists a solution in which the second one is 1. If the original is 0, then there is no way to make this 1. Okay? Okay, that's good for 4, right? What happens if you have an arbitrary number of things? Suppose my actual clause was x1 up to xk. So what I want to do, I'm going to rewrite this as then x1 or x2 or n1 and n1 bar or x3 or n2 and n2 bar or x4 or n3 and keep going till you get the last one, which would be I want to put xk minus 1 or xk, and this would be n, what would it be?
K minus 1.
And I think k minus 2. Yes?
How do we decide values of n?
We don't. Because 3SAT is going to produce whatever it produces. What we've guaranteed is that no matter what 3SAT does with the values of n's, we can always extract back the correct solution for the original clause. Because we just proved it if and only if. If this is one, if and only if this is one. So imagine, for example, if 3SAT does something, right? It produces some answer. What I'm claiming is that if you just look at the values of the xi and throw away all the values of the n's, that will give you the same answer for the original clause. That's the claim I just made, and I proved it. Because I proved it if and only.
So we'll have to try the different values of n.
No, I'm not trying anything. I'm going to let 3SAT do whatever it wants. And then I'm going to say, look at the 3SAT output, take the values of the xi's that it produces, send that back up to the solution for the SAT. Just as it is. Ignore all the n's. They don't affect it. And I just proved why it doesn't affect it. If you had a solution for the 3SAT problem, and you had some value for n, it doesn't matter because you have to get the other ones to work because of the if and only. Yes?
N1 would be 1 instead of 0 in 3SAT. And what?
That would be bad, right? That would not work.
That not.
But I'm saying, what did I say? I said if there is a 1 assigned, if the first clause can be made true, then there exists a way to make the second clause true. I didn't say all assignments will make the second clause true. Right?
There should be at least 1.
There should be at least one. Because I'm saying if SAT could find a solution, I want 3SAT to find a solution. And then I'm saying if SAT can't find a solution, 3SAT better not find a solution, which is also what I mean. But if and only it is very important here. You cannot just prove it one way. Because you want, think of your subroutine. You want your subroutine, if it says yes or no, to trust it. You can't say, well, if it says yes, I believe it. If it says no, I'm not sure. It has to work both ways. Okay, so you have this now. And again, by the same argument as earlier, you can convince yourself that the truth value of this will be exactly the same as the truth value of this, regardless of the assignment of the n's. How many variables did I have to add? I added k minus 2 for a clause of length k. Right? So if I did this for every single clause, and every time I added brand new variables, I would add a whole bunch of brand new variables. But the total number of new variables that I would add is basically linear in the size of the include, which is important because this whole thing has to run in for a long time. And now I have a 3D-SAT instance whose truth value is the same as the truth value of SAT, and my reduction is done. This is a very simple reduction. We check that it runs in polynomial times, in fact linear time. We check the correctness if and only if. That gives the answer. Yes.
Would you say the if and only if statement completely all the way out? Because I'm not sure I want that.
The if and only if statement is, and let's go back to, let me just write it here. That, so we think of SAT as a problem, and we want to know is the answer yes or no. So this if and only if statement we're saying is that SAT equals yes if and only if this part of the reduction is symmetric. Just because I'm reducing SAT to 3 SAT, it doesn't mean that I can just look at one way implication of this thing. I have to look at it both ways.
You have to do the same thing for no.
But if and only if takes care of both cases.
Take care of the no.
Because A, if and only if B means not A, if and only if not B. So that's why the if and only if is important. But it's good. You do have to take care of no's, and that's why we need an if and only if. Because that takes care of both sides. So you can either prove this by saying, there are two ways to do this, right? One way is to say SAT yes implies 3 SAT yes, which is what we just did, and SAT no implies 3 SAT no. This is the way we proved it just now. The other way, you could replace the second statement by saying that 3 SAT yes implies SAT yes. So you can do it any way you want. Depends on the problem. One might be easier than the other. Once you have the first statement, you can prove either of these two second statements, you'll get your if and only if. Right? Doesn't matter which way you do it.
When you say SAT yes is equal to 3 SAT yes.
Implies 3 SAT yes.
So implies 3 SAT yes. I'm not taking what the values of n are. I'm only taking values of x1 instance.
Well, what I'm saying is if the SAT instance is yes, then there exists an assignment of values to variables to make the clauses all true. In that case, there exists an assignment of values to the 3 SAT instance to make that one true as well. So in that case, I only have to show that there exists an assignment to n1 and n2.
There exists an assignment.
That's why yeses are easy to work with. Yes?
And again, that when you say there exists an assignment of n, finding that assignment should be again linear or...
No. I don't care how I find it. I have an oracle for 3 SAT that's already solving the problem for me. Remember, that's how my reduction is working. To solve P, I'm going to solve Q. Solve Q is there somewhere, out in the ozone. It's doing it for me. All I have to do is show that if I could solve Q, I would be able to solve P. In fact, I'm going to show that solving Q is hard. This whole argument shows that solving Q, I don't have a subroutine over there. But I don't need to construct it. All the work is in the reduction. There is no actual solving the problems going on here. We're just deferring responsibility to it.
And if you solve 3 SAT, the number of 3 solved SATs, number of solves you have to do on 3 SAT here is
1.
linear, right?
1. I take 1 SAT instance and convert it into 1 3 SAT instance.
You would 3 SAT instances in this case are at least 4, right?
Where 4?
I mean,
No, I just created, I created a bigger instance. The instance is bigger, only one of it. An instance of 3 SAT is a sequence of clauses, right?
oh,
I've taken one clause and made it into a sequence of 4 clauses here, or whatever, k minus 2. So my number of clauses just got a lot longer, but it's still one instance. Make sense? So I did this trick for every single clause. One clause became an and of clauses. The next clause became another and of clauses. So so maybe I should just draw this out, right? So what's going to happen is that I have my SAT instance here, and this clause is C1, C2, C3, up to Cn, right?
between C1 and C2, do I have
Wait.
an and?
Yes, between C1 and 2, I have an and. That's the definition of SAT.
Okay.
Yeah, that's the whole point. Now this becomes C11 and C12 and C13. This becomes C21 and C22.
Okay.
And they're all added together. So I get this gigantic instance here. And I solve this whole thing. But I've shown that it's not that much bigger. That's very important, because the whole thing has to run the polynomial. Does it all make sense? So I've taken my instance, I've modified it to make another instance, I've done this if and only if thing, I've verified this runs in polynomial time. That completes my reduction. This shows that 3SAT is also NP hard. I want you to think about something. Suppose instead of 3, I said 2. Will this trick work? You're shaking your head there. Can you tell me why?
Well, because like
Let's say I have this one here.
the bottom line, second bottom line, right there.
Yeah, here.
The one with X3 in it. You have to add 2 different variables.
To
so you
pattern out it.
Yeah, you're only pressing one of the literals from the original equation.
And you have 2 more to sort of hook up to the previous and the next one.
So the most you can do it is, the fewest you can do it is 3.
It seems like at least using this trick. There may be another trick, but this trick is not going to work. In fact, 2SAT is polynomial time. These are called Horn instances, for those of you who have done a class in logic. And the way to think about this is that, here's how you solve 2SAT. Suppose you have a variable that appears negated in everything. Then it's easy, set it to 1, set it to 0 everywhere, you're done. Suppose it appears positively in everything, not negated, set it to 1, you're done. So there's somewhere, there must be some, it cannot be the case that this variable appears the same way in every clause. So let's say the variable that appears positively and negatively. It appears positively in this clause and negatively in this one. And there are only 2 things there. Since it's positive here, negative here, you can essentially cancel it out and get a new 2 clause with the 2 that are remaining. You just reduce the number of clauses by 1. And you reduce the number of variables by 1. And you keep doing this and you solve the problem. 2SAT can be solved in polynomial time. This is very, very fragile. You have to have 3. There are many problems like this where you have some parameter k. If k is 2, it's polynomial time. If k is 3, it's not. Or something like that. There's a sharp transition. It's kind of mysteriously cool. Okay. Let's move on. Do you have any questions so far?
That implies there's no polynomial time reduction from 3SAT to 2SAT, yeah?
Well, unless p is equal to everything, yes. If p is equal to everything, then everything just collapses. But yes, in our current state of knowledge, we don't expect to find one because that's what should prove that p is equal to everything. Because then, since 2SAT is solvable in polynomial time, you give me an algorithm to solve 3SAT in polynomial time. Anyway, very good. Yeah. All right. So this was a little fiddly. What we're taking so this was an example of taking a general case of a problem and reducing it to a special case which is still NP hard. This turns out to be useful because sometimes when you want to prove your problem NP hard, you want to start with a problem that's got a lot of structure to it, a lot of interesting information in it. And 3SAT is a bit more interesting than SAT because it's got the special rules and things like that. So this is a standard pattern in NP hardness. To show a problem NP hard, you take a general version of it and try to reduce it to that and see what it works. There are sometimes much simpler versions, and we'll look at another one like that. Let's look at 2 following problems. So you probably remember independent set. Again, my instance is a graph. So it's got vertices and edges. And I have a parameter k. And the question is the largest independent set of size more than equal to k? And again, we really want to find the maximum size independent set, but this is a way to convert it into a yes-no problem, because we like yes-no problems for NP. By the way, if I had a solution to this problem, let's say I have an oracle that can solve this problem, can I find the maximum independent set in a graph? How would I do that? Suppose I could just answer this yes-no question for any k. Can I actually find the independent set in a graph easily?
Yes.
How?
Set k equal to v.
Okay, so what says no?
Then you decrease it by 1.
Right. So you just keep checking until you find it. Right. So that's why this problem is basically equal to that. And conversely, if you had a solution to maximum set, you could solve this problem as well. So they're really the same problem. Okay. This is my instance. This is my problem. And I haven't yet proved this is NP hard. I'm just going to claim it for now. I'll prove it in a second. But I'm going to claim this NP hard. What I want to do is show that this other problem, which again has an instance of G and a parameter K. Have you heard of vertex cover? Have I mentioned? No, I'm not mentioned. Let me define what vertex cover is. So a vertex cover, so let me just say, okay, so what is a vertex cover in a graph? A set S subset V is a vertex cover if for all edges in E, so some edge is equal to U comma V, one of U and V belongs to S. So if you think of what a vertex cover looks like, think of my graph and think of putting marks on some set of vertices that touch it so that every edge gets touched. At least one of its endpoint is hit by one of these marks. That's what it's saying. So it's a weird name, vertex cover. So what it's doing is really covering the edges because I put marks on the vertices to touch every edge. Okay, that's a vertex cover problem. And so the question for vertex cover is, so what's a trivial vertex cover? If I take every single vertex in the graph, it touches all the edges. So clearly the interesting problem of vertex cover is not how big can it be, but how small can it be. Because I take one vertex, it'll just touch the things around it, it won't touch anything else. So the question for that is there a vertex cover S of size less than equal to? Okay. And now what I want to do is I've claimed up front, so I haven't told you why, but I've claimed that independent set is in fact NP hard. So I'd like to reduce independent set to vertex cover. And that will show that vertex cover is NP hard.
So can you define independent?
Oh, sorry. Maybe I should have. Okay, what is an independent set? S So it's helpful when you think about these problems to sort of draw some things out. Okay, so let me just draw some examples. And I want to go to the next page. Let me wait a second. Okay, so I'm just going to note another page here. I'm going to draw a graph. Okay, so here's my graph. Okay, so someone give me an independent set, any independent set in this graph. I don't care what it is, how big or small. 1, 4, and 6. Is there any edge between them? No. So can we get a bigger one? Doesn't seem like it does. Okay, someone give me a vertex cover. It's a little bit trickier.
Second
1, 4, 6 is a different set. Someone give me a vertex cover. A set of vertices that touch every single edge in the graph. 2, 3, 5. So I heard 1, 2, 3, 5, 6, which is true. I heard 2, 3, 5. Then who's it? Is it 2, 3, 5? 2, 3, 5. Okay. So that's the claim is 2, 3, 5. So let's see. 2 touches these 3 edges. 3 touches this one, this one, this one, this one. 5 touches what's left. Seems to work. Okay. Does this tell us anything? Alright, so far we're just playing. We don't even know how are we going to build this?
Compliments of each other.
Sorry?
Are they possibly compliments?
It's a valid conjecture. I don't know. So the claim on the table, and this could be wrong, but that's good. It's always good to have these claims on the table. The current claim on the table is an independent set is the complement of a vertex curve. So it's a clear statement. You can either prove it or disprove it, right? That's a good thing about the statement. It's falsifiable. So let's think about it. What do you think of this claim? Can you prove it? Can you disprove it?
You can disprove it because
Okay, give me an example then.
the vertex cover is all its vertices, and if you take a complement of that, that's not an independent set.
Why is there an independent set? It's empty.
Oh, that's true.
It's a trivial independent set, but it is an independent set. There are no edges between any of the vertices in the independent set, in the empty set. So technically, it's a good practice to check these boundary cases as well. Sounds good. Yes?
If you pick independent set 1, 6.
Pardon me?
If you pick the independent set 1, 6.
Okay, so let's pick the independent set 1, 6. Is it independent?
Oh, I
Yes.
guess that's still vertex covers.
So the complement would be 2, 3, 4, 5. And since 2, 3, 5 was a vertex cover, 2, 3, 4, 5 surely will be a vertex cover. It's just not a small one. But the claim so far has not been that they're, we're just saying that a complement of one is the other. Yes?
Vertex cover includes all those vertices and will include only one of the vertex of an edge, right?
Well, at least one.
At least one.
Could be both.
But what's the point?
That's not, you didn't ask me to justify my existence. I mean, that's not the point here. The vertex cover is required to cover at least one endpoint. If it covers both, yes, it's not efficient, but that's a high standard to set for my poor little vertex cover right there.
So if it is restricted to that, then...
But I didn't restrict anything. I didn't say anything. I just said the claim on the table is not the strong claim you're asking for. The claim on the table merely is the complement of an independent set without your harsh judgment of its quality is a vertex cover.
Does that have to be connected?
Sorry?
I mean, can you just have an edge with or vertex without any edges going to it, and then that would affect your independent set, but it wouldn't affect your vertex cover?
If so, okay, so let's see. So we are claiming, so let's say I have a new graph. Good, this is a good. So let's say I have a new graph that looks like this. Okay, now what do you say?
Well, I'm thinking that would affect your independent set, right? But it wouldn't affect your vertex.
No, but be more specific.
Well, okay, so your independent set would be, if you gave them numbers, I mean, it'd be 2 somewhere on the triangle plus.
Yeah, let me give a number. 1, 2, 3, 4.
Yeah, so you could get 1, 2, and 4.
You can't get 1 and 2. There's an edge.
Right. So you can get 1 and 4.
So I get 1 and 4. Yeah. And what's my vertex cover?
Well, you're right. That's true. I guess your vertex cover would have to be 2 and 3. That's a bummer. Okay.
But this is good. This is all very good to sort of try these cases. I mean, it just helps build intuition. So far, you have failed to defeat the claim. That's fine. That's fine. Okay. Wait. Let's see. Any more? I want to get some. Yes. Okay.
If you add an extra edge from 6 to 7 in the original graph.
Oh, there's a new vertex 7.
Yeah.
Okay.
Then your independent set is 1, 4.
Well, the independent set doesn't change.
No,
adding vertices cannot change an independent set. Adding an edge between 2 existing vertices could change the independent set. But adding a new vertex and an edge to it is not going to change. 1, 4, 6 is still an independent set.
Yeah, but now 2, 3, 5 are not vertex coverage.
But the complement of 1, 4, 6 in this new graph is not 2, 3, 5. It's 2, 3, 5, 7. Foil the game.
What if instead we tried to prove that the complement of the largest independent set is the smallest vertex cover?
Yes, but if you prove that the complement of an independent set is the vertex cover, that implies you're sticking by corollary. Because they're opposite sides. So we can just try to. So when you've beaten up the claim enough and have failed to disprove it, it's time to then try the other tack. You prove it. And then you might fail to prove it, then you go back trying to disprove it again. So go back and forth. Right? This is very normal. This is how we always prove things. Or disprove them. But can we try to prove the claim? So the claim says that a complement of an independent set is a vertex cover. How would we go about proving it if it were true?
So that it's not a vertex coverage.
Sorry?
Assume it's not vertex.
Okay, good. So take an independent set, take its complement. Okay, good. So let's try to prove something by contradiction. So let's say let S be an independent set. Consider V minus S, which is a complement. Suppose V minus S is not a vertex cover. What does that mean? What does it mean for V minus S to not be a vertex cover? By definition, if something is not a vertex cover, it means
Doesn't touch an edge.
There exists some.
there is an edge that has no endpoints in V minus S. Okay, so there exists E with no endpoint in V minus S. If E has no endpoints in V minus S, where are its endpoints? Therefore, E has both endpoints in S. That's a problem, isn't it? Because we said S was an independent set. You cannot have edges between vertices in S. That's a contradiction. So if S is an independent set, and you look at V minus S, it has to be a vertex cover. So the claim is actually true. Anyone? Okay, good. Woohoo! We've shown a complement independent set vertex cover. How on earth is going to help us with the reduction? Let's go back to our question. Does this help us? I didn't talk about max. Does there anywhere in the statement say max? No. If you have a graph where the largest independent set has size more than k, what can you say about the vertex cover of this graph?
But then it's just going to have a size of less than k.
Less than?
Less than k.
Size of n minus k.
Yeah, of a size. It's going to be small.
Good enough. It's going to be small. But it's precisely it's going to be n minus k. If the largest independent set has size less than k,
it's going to be bigger.
The minimum vertex cover is going to be more than n minus k. So here's our reduction. I told you it was going to be easy. So given a graph, so this is my independent set instance, it's a graph and a parameter k. Here's my reduction. Copy the graph over and replace it by n minus k. Hopefully you can see this runs in both of them. That's it, I'm done. This reduction is completely trivial because we have shown that the two things are complements. We know now that to prove the point, if IS is greater than or equal to k, we know that vertex cover is less than or equal to n minus k because of the complement property. If IS is less than k, we know that the vertex cover is going to be greater than n minus k. If and only if. Reduction runs in polynomial time. We're done. Because we understood the structure of vertex cover, the unknown problem. We played with it. We looked at how it related to it. Okay, take a 2-minute break. Let's contemplate this.
Yes, so I think I understand this, but it seems too easy.
There's no equal, there's implication. Oh. No, it's correct. That's correct. So the strict equality is strictly equal.
So basically, if we have a problem B, we don't know how difficult it is. Well, we can reduce it to Q. We can essentially say that P is, we can reduce.
If we have a problem Q, we don't know how to do this. We take a problem we know is hard, that's P, and reduce P.
We know it's hardness.
We know P is hardness and reduce it to Q.
So we know that Q is at least as hard, or at least as easy.
As hard as
It seems easy to try to make sure it's being deceitful.
That we or other languages.
So it's really similar to the other. We're trying to show this.
So we have P. We don't know how hard. That means we know that P is at least as hard as Q. Yeah. It might be easier. But it's not hard.
Let's continue.
Because we can solve.
So let's draw the picture of what we have so far, right? So I showed you a reduction from SAT to 3 SAT. This symbol is a reduction, which is very confusing. It looks like less than equal. We don't think of it that way. It's more like a curve, thing like that. And then we also showed that independence of the set. This operation of reduction is transitive. If A can be reduced to B and B can be reduced to C, then A can be reduced to C. Again, if you think of some subroutines, that makes sense. If I have a big subroutine, if I have a big routine for A, inside I call a subroutine for B, and inside I call a subroutine for C, then obviously I've got a mapping that goes from A to C directly. So to connect all the dots here, to show that vertex cover is in fact NP hard, I need to sort of create a line from here to here. And that's what we're going to do now. We're going to show that 3 SAT reduces to independent SAT. Okay? And this is an example of a slightly trickier kind of reduction. So we're seeing, okay, the first reduction we saw from SAT to 3 SAT was going from general to special. Right? The second kind of reduction from independent SAT to vertex cover was using some nice structural property to basically say that these are essentially the same problem. One's a complement of the other. And if you're lucky, that happens sometimes. But by far, unfortunately, the most common kind of reduction is the kind we're going to see now, which is 3 SAT independent set, where you basically have to roll up your sleeves and grunge through an entire, very, very disgustingly boring thing that's 10 pages long sometimes and it's hard to read. In this case, it's generally very hard. And this is called a gadget-based reduction, where you methodically transform your input problem into the output problem, bit by bit. And we'll see how that works here. Okay. So this is what is called this is what is typically called a gadget-based reduction. And you'll see why. Basically, what we're going to do is we're going to make some widget to represent a clause. We're going to make some other widgets to represent vertices, to represent variables, and we're going to put some more widgetization to make sure that you can encode true and false in this weird construction. So it's like building, you want to build a 3 SAT block with independent set Lego bricks, and it's going to be very painful. So let's see how this goes. So the first thing we have to decide is, okay, what's a variable? Right? How do we encode a variable in the language of graphs? And to do this, it helps to think about what is it we're doing. When we solve 3SAT, what does the solution look like? It looks like assignments of values to variables, true or false. Well, true or false kind of looks like zeros and ones. And zeros and ones kind of look like picking and not picking. In a dependent set problem, we're picking versus not picking. So this tells us that somehow we want a variable in 3SAT, the thing we pick to be 1 or 0, to kind of look like a vertex. The thing that in independent set we pick or don't pick. Right? But if we say that a variable is a vertex, do we have a vertex for x and another vertex for x bar? Well, we're not quite sure yet. But if a variable is a vertex, what's a clause going to be? It's going to be some collection of vertices hooked up together. And in fact, here's what you do. So our reduction is going to say for every literal, not every variable, but every literal in a SAT instance, 3SAT instance, we're going to have a vertex. So in other words, if I have clause C1, which has literals x1 or x2 or x3, let's just think of them as a variable. So let's put the clause here. And I have clause 2, let's say, which has x1 bar or x4 or x5. Let's just repeat. So what we're going to do is the following. We're going to rewrite this clause as 3 things connected together. Right? We're going to call this x1, we're going to call this x2, we're going to call this x3. Okay? And we're going to do the same thing here. Okay, but remember the first basic property of a variable, right? Either you pick it, or you set it to 1 or 0. You pick it or you don't pick it. In my independent set language, how would I capture the idea that x1 and x1 bar can't both be 1 at the same time? You put an edge between them. What would that do?
And you can only choose one or the other, and you choose this.
Exactly. So now I'm going to put an edge here. So let's say I have 2 clauses. This is the graph I'm going to produce. Okay? And here's what I'm going to claim. Okay. So if I can satisfy a clause, what does it mean? That means at least one of the variables in that clause is set to 1. Right? That means I pick at least one of the vertices in that group of 3 to be set to 1 because I picked it. That's what my idea. I'm not proving anything yet. I've just got this big idea in my head of what this might look like. Can I pick more than one thing in that group to be 1? Well, it's a clique. You can't pick more than one of those things to be 1. They're all connected to each other. So I can only pick exactly 1. Okay, that's fine. So for every clause, I will pick exactly one of those 3 things. Right? If I have n clauses, how many things will I end up picking? If I could actually make it satisfiable. I pick n things, right? So in some sense, if this is satisfiable, I should be able to pick n things there. Or it seems like it anyway. And if it's not satisfiable, I should not be able to pick n things there. So now we have a sort of a working argument that might lead to a proof. We have a way to connect satisfiability here. Everything is satisfiable to a size of an object n things that are all distinct. Okay? So we have clause gadgets, we have variable gadgets, we have constraints that we satisfy. The idea that you can't pick x1, x1 bar at the same time by putting an edge between them. We've expressed the language of logic in the language of a graph in independent sets. And that's where the hard part of these proofs comes along. This problem you don't know how to solve, you have to use this language to express this other problem. Usually it's often 3 SAT is a problem. So given this intuition, and when you start trying to prove these things, this is how you build up some intuition. We can now say, okay, let's construct an actual reduction and then see if this works. Just like with the claim, it is helpful to have a reduction and prove it wrong and then modify it rather than just being yes.
Could you just not connect the 3 points?
Could I just not connect the 3 points?
So the
that might work.
X1, X2, and X3 bar.
Just don't connect them. You could. Then you'd get exactly 3 for every clause. And that seems like it might work as well. Maybe. Okay. So, yeah, let's just continue doing this thing and see what happens. Okay. So I'm going to construct a proof and we'll see if that proof breaks or not if you don't put edges. Okay, maybe right. So this is what our reduction is going to look like now. So the actual proof is going to be given a collection of clauses. So you have C1 and up to CK. Okay. So we say that assign vertex to each literal of each clause. Right? Connect two vertices if their literals, their corresponding literals, are in same clause. That uses the triangle. And this is the part we could omit if we want to try it. Or they correspond to negative and positive versions of same variable. Okay? That's the first part of reduction. And the claim is the set of all the CI is satisfiable if and only if the independent set of this graph has size more than, let me make that name. Okay? So this is a proposed reduction. I'm not saying it's correct, but I'm saying this like this. Okay? And now we have to prove it. So again, it's an if and only if. So let's assume that, so part 1. Let's assume that, in fact, the clause has value. So let's say.
I think I see now why my idea won't.
You do?
Yeah.
But I don't.
So I think the reason why is if you don't connect those vertices, then you could have an independent set of size more than m by selecting multiple vertices that correspond to a single clause, but not satisfying the other clause.
You could omit 2 clauses and pick up the slack with another one.
Yeah.
Yes. This forces you to have a one-to-one assignment between clause satisfied and vertex vertex of independent set picks with counts match. Okay. So let's do this way. So C satisfiable implies I as greater than equal to. Okay, now let's go back. So this is a reduction. What we wanted to prove is that if the set of clauses was indeed satisfiable, then you can compute an independent set of size more than and maybe we should go back even one more just to look at the picture. No, that's not what I want. Wait, what just happened? So this is so you can keep this picture in your head to see what's going on. So suppose this clause set is satisfiable. How do I now produce an independent set of size more than n? At least n. What do I do? I need a method to take the output, because it will satisfy it, and construct that. What am I going to do? Remember, our intuition in building this reduction was somehow that setting variables to true was like picking a vertex. That was our basic idea. So what should we do? So let me claim the following. I'll say, take for each clause, take a literal that's set to true. There must be at least one that's satisfied. Pick that corresponding vertex to be in your independent set. Do this for every clause.
Am I taking the three verses randomly?
No, I'm saying take one of them. If look at all the literals that are set to one, there's at least one. There could be more. If there are more, that's fine. Just take any of them. Any of them, not randomly. And then pick it to be my set. So in this case, so give me a satisfying assignment for these two. Tell me what would be a good way to satisfy them. So let's say I put x1 is equal to 1, which makes this 0. So this is satisfying. So I can make these two 0. Let's say it's 1, and I'll make this 0. Or in fact, I think this one as well. This is satisfiable? Yes? So let's say this was the output we got when we said this was satisfiable. So now I'm saying, okay, let's go pick the x1. And now I pick one of these two, I don't care which one. So I'll just take x4. Is this an independent set? Yes. It is. Proof by example.
Yes.
But that's the idea, right? We want to claim that this always works.
But if there's an edge between x1 and x4, how do you make sure?
Why would there be an edge between x1 and x4? Remember the construction. We only have edges between things in the same clause. Or if it's the same variable, it's just complementary. And x1 in clause 1 and x4 in clause 2 will never be connected by an edge, by construction. Yes?
Can that be self-reduced?
My reduction did not specify the ability to produce a self. My reduction was very clear. Connect up the three things in a clause, right? And hook up across a triangle only if you're the same thing, just complementary. The reduction is very specific. So there is no way to get a self-loop because you will never do that. So because of the way we constructed this graph, we know that we're going to produce n things because we're picking one from each clause. That part is fine. Can we prove that these n things form an independent set? Well, how? How do you prove that? Sorry? Very good, by contradiction. Suppose not. Suppose there was in fact an edge between the two things in the set. Now these two cannot be in the same triangle because you wouldn't have picked them, you only picked one from each triangle. So they have to be on different triangles. But if you pick them and they're different triangles and there's an edge between them, that means they're the same thing and one is x1 and one is x1 bar. But that means one is 1 and one is 0. You would never have picked them both. You only pick the things that are set to true. Therefore, it has to be. That makes sense? So, again, the claim is, the proof is, take in each clause any literal set to 1 and add corresponding vertex to is. Size of is is greater than or equal to m. In fact, it's equal to m. And it is independent because of what it is. Okay, that's one side. What about the other side? Now what do I do? Suppose I have an independent set of size more than n, at least n. how do I construct a satisfying assignment for my clauses?
Take each vertex.
I have to make only one set of clauses.
I need to construct some satisfying assignment. Yeah.
Then
So the first observation we have to make is that you cannot pick more than one vertex in each triangle, because then it wouldn't be independent. So now we have one vertex for each triangle, exactly one. What do we do?
We'll add 2 more auxiliary vertex.
Why? I have one vertex from each triangle, right? What should I do now? Well, how should I construct the assignment now?
put each vertex in each different clauses.
I have one vertex in each of the different triangles, yeah. And then
take the negative of the other clauses and put it in the negative.
I have one vertex for each of the triangles. What do I do?
-1.
Set those literals to 1. Remember, our whole basis for this reduction was setting to 1 corresponds to picking. I just picked. Set them to 1. So the claim here is there exists there will exist exactly one vertex picked in each triangle. By the way, why is that true? Why? How come? Why do I? If the independent set is more than m, why do I have one each triangle? By the Pigeonhole principle, I can only pick. I can't pick more than one per thing. So if they're m, you have to have one from each of them. That's an important point. Otherwise, I don't want to have missing triangles. So one in each triangle. Set corresponding literal to 1.
Do we have to specify that the independent set is maximum?
No. Did I say maximum? I just said it's more than m. That's all I'm using now. There is no maximum here. These are all decision clauses.
And m is the number of clauses?
Yes, by construction. Design very carefully. Everything has to work just the right way. So now if we go back to our example here. So pick an independent set, anything you want. Pick an independent set in that graph. Anyone?
Just vertex x1.
Sorry?
Just vertex x1. That's the independent set, right?
Of size more than m.
Oh.
Size more than 2. Pick an independent set of size more than 2. Anything you want. Come on, any independent set, size 2.
x2, x4.
Sorry?
x2, x4.
Okay. So let's say I pick x2 and x4 as my independent set. So what am I saying? First of all, because I picked 2 and there are 2 triangles, I get 1 from each triangle. I go look at that corresponding literal and set that to 1. So this becomes 1 and this becomes 1. And set everything else to, I don't care what you set everything else. 0, 1, I don't really care. It doesn't matter because every clause has now become 1. And I've satisfied my set of clauses. And again, I can do this because I never pick 2 things that would contradict each other. I never pick x1 and x1 bar because they would not be part of an independent set. So this assignment is always valid. I'm never going to set something to 1 and something else to the same thing to 0 somewhere else. So it's a correct assignment.
But the second part of the proof, you have to show that each clause has at least one vertex from the independent set, right?
Right, because I said that. Exactly one vertex picked from each triangle. Each triangle corresponds to one clause.
Okay.
So that proves that.
But that should be the proof, right? Not this way.
You need both ways. You gotta have both ways. That satisfiability implies a good independent set, and a good independent set implies satisfiability.
Yeah, but you have to show that a good independent set means
Satisfiability.
Yeah.
it's like. But you still have to construct the clause in such a way that each.
No. The clauses are given to me. I'm not constructing the clause in any way. I'm constructing the assignment of values to the variables, and that's this.
Oh, the construction has been done.
Yeah. Yes.
So I'm just thinking like in this case the independent set can be greater than n. I think this cannot be greater than n.
It cannot.
Should be equal.
Right. But my problem statement for independent set is there an independent set of size greater than equal to n? So I'm just keeping it that way because I'm talking about that. I'm not talking about exact. In this case, they're the same thing. You're right.
You can consider more blocks inside.
Huh?
You could have had more blocks which we left out.
No, my construction is very specific. I have exactly one triangle for each box. I'm not looking at an arbitrary instance of interest. I'm looking at a very specific instance of interest. Yeah. All right. Well, again, these things, they take time, they take practice, they take some reading. The notes actually have all these examples and some more. They get more and more baroque as you go along. This is still well preserved, relatively simple, but there are some more complicated ones. It's one of those things where you just, they just grow on them. All right. Yeah. One last question, and then we'll do. Yeah.
Is it always possible to create a tree-like structure from a graph? So that you can transform it. I mean, finding an elevator is a problem to a three-set problem.
I'm not doing that. I'm doing it the other way around. I'm doing 3-set, 2 independent set.
So this is very specific example. I mean,
Yes. This is a very specific construction of a specific graph that has this property. But that's okay. That's all I have to do. Given a given an arbitrary 3-set instance, I construct a specific independent set instance. That's why it's asymmetric. If I do it the other way around, I take an arbitrary graph and construct a specific 3-set instance. Okay? Alright. See you all later.